I believe you wonder, what more? What more could we do? Well, we have the biggest surprise for you. Indeed, Professor Kevin Warwick, Professor of Cybernetics in the University of Reading in the UK, where he carries out research in artificial intelligence, robotics, and cyborgs. He was born in Coventry and left the school to join British Telecom at the age of 16, and at 22, he took his first degree at Ashton University, followed by a PhD at Imperial College London. He has published over 500 research papers, and his experiments in implant technology promoted his featuring on the cover stories of many US magazines, where I had the chance to first get to know him from these magazines. He was awarded DSCs by the Imperial College, the Czech Academy of Sciences, and honorary doctorates from Ashton and Coventry. He received the Future of Health Technology Award at MIT, the Mountbatten Medal, and in 2000 he presented the Royal Institution Christmas Lectures. Now, his most recent research involves the invention of an intelligent deep brain stimulator to counteract the effects of Parkinson's disease tremors, which is a topic that was just being discussed. But another project involves the use of cultured neural networks to drive robots around. Now, although he's known for all these pioneering things, and he'll have probably much more to tell us, he's actually the only person in the world who is truly a cyborg. He's done a pioneering experiment which involves a neurosurgical implantation into the median nerve of the left arm to link the nervous system, his nervous system, directly to a computer. So now we're not talking about hypotheses, we're talking about the man who's done it all. So please join me in welcoming Professor Kevin Warwick.
Thank you very much for the very kind introduction, and thank you for inviting me here. It is, as Miguel said, an enormous honor, and it's an honor to follow Miguel. Excellent presentation, and the speakers before him, so they don't beat me up or anything like that. Right, I've called this the Cyborg Experiments, and if you're not familiar with the term cyborg, there was a documentary film a few years ago, which some of you may have seen. It was called The Terminator, and there was an American politician in the film, of course, a guy called Arnold Schwarzenegger. And in the film, a cyborg was defined as a cybernetic organism, part human, part machine. And we've seen some examples to that end in terms of animals and machines. I'm going to describe 3 different experiments, part human, part machine technology, part animal, part technology, all in this vein. The first of them, following on to some extent with what Miguel was talking about, is looking at a robot, but a different form of robot, as we will see. First of all, though, I want to introduce you to some of the robots that I get to play with in my university. The first of the robots we're going to see is called Morgui. Morgui is a robot head with 5 senses, and what we're trying to do is to fuse the data, to integrate the data from the different senses. But it's more the little wheeled robots later on that are of interest to what I'm going to talk about. So this is actually taken from a BBC program called Inventions That Change the World. And there is sound. Please.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books. No, it don't, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher,
yes,
where are these in terms of, are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't.
They have some innate abilities.
There's no self-preservation with that.
Well, we do have the power supply. They don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food.
But if you turned off this section of the floor,
if we turn off this section,
here,
they have a basic instinct to go and look for some power somewhere else.
They
will keep going to do that until they find some.
So if I put him down,
it should go off.
So he'll have to go and look for power. And are you going to tell him to do that?
No, it's an innate response for that robot. It's a basic thing of his life. Yeah.
No, his lights have come back on.
Lights have come on.
So he's found power.
He's happy now that he's getting power. Away to go.
But these then are as intelligent as slugs.
It's different. But in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
If any of you are Wikipedia aficionados, you'll know the original definition there that I gave was that our robots have 50 to 100 brain cells, which is about the same as a slug or a snail or a Manchester United supporter. But the BBC didn't like that bit at all. Those robots have microprocessors to control them, but we can look at how they learn and how they adapt and how they teach each other. They can communicate with each other using infrared, but they've got microprocessors for their decision-making, their brain. The latest robots we have don't have computers for a brain. The right-hand side on this schematic is the robot body. So we saw the little robots with wheels, and they have ultrasonic sonar sensors. The left-hand side, this is a multi-electrode array. This is an array of electrodes on which we are growing a brain, a biological neural network. What we do is take neurons, brain cells, from a rat. We separate them using enzymes, and then we lay them down on this multi-electrode array. So here in these are called Potter rings to stop any liquids getting out, to stop evaporation and so on. We take the neurons, lay them down in there. Within about 20 minutes, the neurons are starting to connect up with each other very closely. They send out, first of all, little protrusions that eventually, when they connect up, become the dendrites and the axons in the brain. We have something like 100,000 neurons. After about 1 week, they have grown in a two-dimensional array into a brain, which we can stimulate. We can send electrical signals to the brain and monitor where it gives an output in terms of action potential type signals. We then feed that back to the robot body. So the sensors from the robot stimulate our brain, this biological brain, and the brain then makes a decision to change the direction of the robot. So what we're going to see here, this is the robot body. These are the ultrasonic sensors. What this robot is supposed to do is to move forwards. When it gets to a distance from the wall, the brain will receive a signal, and what we want it to do, like that, is to move to the right. So it's a very simple task. And then we see it moving when it's not supposed to. And then we see when it is supposed to move, it doesn't. This is it's like a 2-week-old robot. It's a baby robot that is just starting to move around. And so you look at it and it's got a mind of its own, this robot. Well, it has got a mind of its own. That's the whole point. What we can study is how the robot improves in its performance over a period of time. A process called habitual learning. It's called Hebbian Learning. We can actually see under the microscope the neural connections strengthening, being made, that makes the robot better at doing that. One reason for doing this research is to try and understand more how memories are formed in the biological brain. If we can put the robot in particular positions and see how the memories of those positions appear in the brain, then hopefully we can understand what exactly memories are a little bit more, how they are recalled, and so on. Clearly, it has influence in terms of our understanding for Alzheimer's disease, ultimately. Can we effect a cure by altering the neural makeup? The way that this research is going as I speak is, first of all, not just culturing, growing the brain in 2 dimensions, but culturing it in 3 dimensions. That gives us a brain not of 100,000 brain cells, but of 30 million brain cells. So much, much bigger, much more powerful, and clearly it has lots of things we will need to make more sensory input, we need to give it more stimulation and so on. The other way we're taking it is to not use rat neurons, but to use human neurons. These are neurons taken from human embryos, and they are being cultured to put in the robot body. So very soon we will have a robot body of this type. I mean, it could be a walking robot of the type that you've seen before, but with 30 million human neurons. And clearly some of the questions that have been raised before by the speakers in terms of brain and body, I mean, this is looking at growing a human type brain, but in a robot body. The value of the body is what the brain makes of it, as you've heard. The next set of cyborg experiments is in terms of changing behaviours with the human brain. And many of you may have seen experiments of this kind with electrodes positioned on the outside of the brain. In the right-hand image, I mean, it looks great for magazines. What the research is in that project is trying to pick up how different music affects different parts of the brain. So whether Beethoven will excite certain neurons and a pop singer will excite other, Kylie Minogue or whoever it happens to be will excite other neurons. It's looking at how brain activity is affected by music. I think this is probably standard, the left-hand one, in quite a few research groups. Electrodes on the outside of the brain trying to pick up activity, and the researcher will try and learn different ways of thinking to drive a little robot buggy around. And as we've heard, you've got all sorts of different neural activity. It's even for basic motor movements, you're getting neural activity all over the place. These electrodes are picking up particular neural activity, but from millions of neurons near the surface of the skull and operating in a particular direction. So it's very limited. And you find with researchers that maybe the researcher can think in a certain way, and 8 times out of 10 the little robot will go in one direction they want it to, but then twice out of 10 it goes in completely the wrong direction. In fact, the American military tried just this sort of interface quite a few years ago now for fighter pilots, for them to learn how to think in order to fire a missile, because in the time it takes to press the button to fire the missile, you could be shot. So if you can fire the missile just by thinking about it, using electrodes like this, it would be excellent. What they found, the fighter pilots could learn to think and yes, and fire the missile, but then they thought about going home and having a beer, and it fired the missile. So it's not good for fail-safe things for a number of reasons. Really, we need to go that step further. Either electrodes positioned on the brain or electrodes into the brain. Firstly, for monitoring what's going on, but also for changing what's going on. Now, in terms of changing what's going on, we've just seen a mouse being affected by electrodes. Well, there is a commercial product for Parkinson's disease using deep brain stimulation. And before I talk about the research we're particularly doing on it, I'd like to show you what the possibilities are with deep brain stimulation. What you're going to see is a guy who has Parkinson's disease. He has received electrodes positioned deep in his brain, in the subthalamic nucleus. You'll see the person with Parkinson's disease, then you will see the assistants switch on the power packs. Now, anybody who's interested in evolution will have noticed that for humans, we have a lot of space here. There's not really much going on in our body here. Well, what this is for is actually for putting pieces of technology. It's a marvelous aspect of evolution. And you will see the assistants switch on the power packs. The power packs are positioned, implanted here, with wires running up underneath the skin into the electrodes deep in the person's brain. So this is an actual person with Parkinson's disease. If you've never seen it before, what you're going to see is with Parkinson's disease and then with the stimulators operating.
In 2 minutes, what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain. And you see that in a few seconds, the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, he moves, and he resets himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer, does he say? And he will show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, this is a commercial product. There are many, many people that benefit from it. One of the problems with it is that it's actually applying a current, quite a heavy current, into the brain all the time. It's stimulating all at the time. And in fact, the patient doesn't want to switch it off, because if they switch it off, they then have Parkinson's disease again. The problem, therefore, is the power packs run down, and it's very difficult, impossible commercially, to recharge them externally. What has to happen, therefore, is the patient goes back into hospital, they have surgery for the power packs to be removed and fresh power packs to be put in place, just like if you're changing a battery on a torch or something like that. This all costs money, and of course there's the possibility of infection creeping in just for the operation to have the power packs replaced. So we are working with Tipu Aziz, who is a neurosurgeon at the John Radcliffe Hospital in Oxford, to try and make the stimulators intelligent. So the stimulator only stimulates when it needs to stimulate, not all the time, and then stops, which will potentially allow the power packs to be used for many, many years, 10 years, 20 years, maybe more. But the stimulator not only needs to know when there are tremors occurring, it needs to predict when tremors are going to occur before they actually occur. It needs to be intelligent. And what I've got here are these are signals taken from a patient. This is the EMG, this is the muscular data over a time sequence. So what we can see for this Parkinsonian patient, there's nothing much happening, and then here, this is where the movement, the tremors, actually kick in, and we can see the measurement of those. This is the time sequence, exactly the same patient, the same time, and this is data, electrical activity taken from their subthalamic nucleus. This is electrical activity taken from deep in their brain, from the electrodes that are positioned there. And it's difficult to see too much from it. Maybe we can see about here, when the tremors start off, the variation, the standard deviation of the signal reduces. So here the signal varies much more than it does here, and the second part corresponds to when there are tremors. What we've done is to feed this electrical data into a fairly straightforward artificial intelligence system. And we can see the output of our artificial intelligence system on the top line. And here, the network has been trained to recognize tremors. We can see 45 seconds, 50 seconds, the output goes high. This is like our artificial intelligence system waving a flag and saying there are tremors going on. Okay. More important, here, 14 seconds we see a spike, 19 seconds we see a spike. The network, our artificial intelligence system, is saying something is happening. And checking down here, we can see the electrical activity changes a bit at the same time, and even it looks as though there is some sort of movement. It's as though the tremors are trying to start but don't get started. This is the most important one here. 30 seconds, a big spike. There's nothing happening down here. There's no movement at all. And this is what we've now got. We've now got this spike on AI systems trained on lots of different patients. About this time period, 15 seconds or some 10 seconds, is that sort of 10 to 15 seconds, what it appears to be is a prediction that tremors are going to happen. We are, ourselves and the surgeons are convinced enough of that we're now undergoing tests with actual patients so that the stimulators only switch on when we get this predictive signal. And the research is now looking at what frequency of signal, how long do we need to stimulate before the tremors stop. But it's interesting, the 10, 15 seconds ties in exactly with Miguel's 10 seconds or so he was saying with the mouse. So it's that sort of time period. And this is interesting in itself, because what it means is that something is going on deep in the person's brain, electrical activity, that 10 to 15 seconds later will result in the tremors starting. The person themselves doesn't know that, but our artificial intelligence system does. In a way, the artificial intelligence system is outthinking the human brain. And here we can see an application for it to counteract the effects of tremors. The same stimulator, the same piece of technology, is in fact used in a different part of the brain to counteract the effect of epilepsy, of epileptic seizures. And again, we are looking at the same sort of data for epileptic patients. There, though, it appears we're not dealing with a prediction of 15 seconds, but even minutes, that we can get an analysis which says, from an artificial intelligence system, in a few minutes' time, this person is going to have an epileptic seizure, which could potentially allow them to sit down and relax, or whatever it happens to be. Interestingly, the same stimulator is used for people that have clinical depression. And there, when the stimulator is used, the person describes it as a black cloud lifting. Suddenly they feel fantastic. Now, we're not actually looking at research here, but it's interesting to speculate that if we did actually predict when somebody is going to be depressed, that we could feed that into the stimulator, so somebody with depression could be walking around and suddenly the stimulator comes on and, oh, they feel wonderful, and then think, oh, that means I was going to be depressed. Oh, so I don't know whether it would work. The final set of experiments to talk about borders this gap. I mean, we've been hearing a lot about the use of different technology, chemicals, pharmaceuticals, and implant technology for therapy. There we saw helping people with Parkinson's disease, so more therapeutic. But clearly it opens up the possibility of enhancing humans, giving humans abilities that we don't have. What do I mean by that? Well, even way back, 16th century, people were looking at how limited, this was a statement from Francis Bacon, the dullness, the incompetence, how senses, human senses, are deceived. In fact, our senses, we can sense about 5% of what is going on around us. There's all sorts of information, infrared information. I mean, for example, your television set senses in infrared. You don't. Surely that makes you feel jealous every time you try and control the television set. Why don't you have an infrared sense? Enhance, have an infrared sense. We have the technology. Or ultraviolet, or ultrasonic, or X-ray. All of these senses potentially we can have. And we can see how the brain can take in different information. We've been seeing that, we've been hearing about that in previous presentations. Memory is another one, particularly those of us that are getting older, we keep forgetting things and so on. Well, why not have a piece of technology that works as your memory? When we compare human memory with computer memory, there's no comparison, it's a different league. The computer, in most cases, is networked. Your brain is not networked. Why not? Network your brain. Have memory that's across the internet. Why be limited by a very small, finite amount of memory that you have in the human brain when you could have something much, much more? Biggest thing of all for me is communication, and I'm amazed that humans still put up with the pathetic form of communication that we have. When you think about it, we have highly complex electrochemical signals in our brains, all sorts of ideas and thoughts, colours, images, and so on. And when we want to communicate those ideas to somebody else, what do? We translate those complex signals into trivial, coded messages, mechanical signals. That's what my mouth is doing now. Very, very slow sound waves eventually travel to somebody else's ears that convert them back to electrochemical signals. And of course, anybody that is taught in a school or university knows you can tell the students something time and time again, and it comes to the examination. Have any of them paid any attention at all? If you could just send the signals, zoom, to their brain, well, you'd know they would know the information. And importantly, if you could send them like that, it doesn't have to be in serial form, which of course is very slow, very error prone. It can be in parallel, lots of messages zoom, at the same time. We won't need to have examinations anymore. We'll have a whole new form of... Let's enhance, let's upgrade and communicate in a reasonable way like computers communicate. This therapy enhancement problem we see here, this is Campbell Aird. He lost his arm due to cancer and he's been given this robot arm, but you see he has to operate his robot arm. There we go, flicks a switch to move the wrist, and he'll flick the switch again to move the elbow, which is a great shame. It would be much better if he could operate this arm directly from his brain and to receive sensory signals from the hand, from the arm to his brain, and that needs a bidirectional interface. The wires, electrodes from his brain, from his nervous system to the wires. And then, if we have a bidirectional interface, we can give somebody a replacement arm. This is therapy. But we don't have to just do that. What we're talking about then, if we do that, are brain signals, neural signals on the wires. And if we've got those sort of signals on the wires, we can plug into them, send them over the internet. We can have this hand on a completely different continent. We can have this hand on a completely different planet. And the senses, when this hand grips an object, the signals can be sent back across the network to the person's brain. Your body does not have to be where your brain is. Your brain can be in one place and your body can be all over the place, wherever the network takes it. That's enhancement. So what have I done in that vein?
Now prepare yourselves for this. A British scientist has become the world's first bionic man.
It's true. Cybernetics Professor Kevin Warwick has had an implant attached to his nervous system. We'll have a look at it in a minute to discover exactly how the brain sends out signals controlling movement and even sensations such as pleasure and pain.
The secret operation involves surgically inserting an implant and cable into the left arm of Professor Kevin Warwick.
Well, the operation's been going about 10 minutes now. Spoken to Kevin, everything's going fine from his end, and the implant will shortly be about to go in.
The implant was fired onto a main nerve near the wrist. Wires from the implant were then threaded through a cable beneath the skin, exiting further up the arm to an electronic connector.
Effectively, what we've got is a link from my brain down the median nerve, through the wires and out to the connector. And then in the weeks ahead, we'll be putting on our radio transmitter receiver that we've developed at the university, and that'll be making the link by radio from my nervous system to the computer and back the other way.
This is what everyone hopes to see, nerve signals resulting from finger movement or even emotions. The medical aim is to help people who are paralysed, although some experts are unconvinced. But Professor Warwick is used to detractors, and experiments linking his nerves to a computer will begin soon. Sue Nelson, BBC News.
So, what did we actually do? Well, it was a 2-hour neurosurgical operation. It was a research project for the surgeons involved because no human had had one of these implants at that time. What was implanted was this. This is 100 electrodes, 4 by 4. Each of these spikes is 1.5 millimeters long. The electrode tips themselves are actually 1 to 3 micrometers. At this time, it was called the Utah Array. It since then was rebadged, renamed as the BrainGate system. So whichever you come across, it's exactly the same piece of technology. And this was fired into the median nerves of my left arm. Now, the median nerves are the main bunch of nerves that move from your brain to your hand and then take sensory signals back the other way. So you've got motor signals and sensory signals, which is quite useful if you want to research with an implant. I didn't have a medical need for this. This was purely a scientific piece of research. And this was fired into the median nerves. The median nerves are about 4 millimeters in diameter, all of them, very, very small nerve fibers. So this 1.5 millimeters went in almost halfway into my nerve fibers. This is a little picture from the operation. You can see what they had to do was to make 2 incisions. This is the incision by my wrist there, I'm pointing, that's there. They then pushed that tube down between the incisions so that they could move that 100 electrodes down the tube. They then removed the tube, hammered the electrodes into my nervous system there, and I then had wires running up my arm onto this connector pad. And that's how I was for 3 months. So when I moved my hand, my neural signals, the sort of action potentials that we've been seeing before, we could pick up clearly, very different from other signals, on these terminals and send them to the computer, either by wire or by radio, and then send signals down from the computer, biphasic, positive, negative signals, to stimulate my nervous system, which over a 6-week period I learnt to recognize the pulses. So it was both ways, signals out, motor signals, and sensory signals in. I've got a little video clip from Discovery TV to show you some of the things that I was able to do.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, Cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time 2 people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman.
So now you know. A few holiday snaps to finish with. This is with the implant in place, wearing a blindfold. On the baseball cap are ultrasonic sonar sensors, the same sort of sense that a bat has. The output of the sensors was fed down to stimulate my nervous system. So what was happening, as an object came closer to me, my brain was receiving pulses of current that increased in frequency the closer an object came. And as an object moved away, the pulses of current died away. So ding, 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 and then ding, 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 back the other way. But I had learnt over a 6-week period to recognize these pulses. So with the blindfold on, as I moved around, I could detect objects pretty accurately when there was a slight movement closer or further away. So here you get the therapy is using this to help people who are blind, to give them a different sense. But for all of us, it's enhancement. It's giving, you know, we can all have, if anybody here wants an ultrasonic sense, you can have it. Let's plug an implant in and have an ultrasonic sense, experience it. This is my wife, helped in a number of ways with the project. She's wearing some jewellery that a student at the Royal College of Art put together. It actually changes colour from red to blue. There were a number of ways that it could operate, but it was linked to my nervous system. So my nervous system was controlling the colour of my wife's jewellery. Now, when you're measuring signals on the nervous system, of course, there's all sorts of signals that you can get. Ros Pickard at MIT is measuring anger and stress in drivers. If I was to go, ah! So, if I was measuring shock, I could have, hopefully you'll agree with audience participation, I would have measured the, sorry if I woke anybody up, and sorry if anybody has peed themselves. I didn't. Now, in this case, if you can imagine, please, when I am calm and relaxed, my wife's jewellery is blue. And if I get excited, my wife's jewellery flashes red. She is in a different place altogether to me. The jewellery is blue. Okay, fine. He's not doing anything he shouldn't do. Suddenly, the jewellery starts flashing red. What is he doing? And more importantly, who is he doing it with? Hopefully she trusts me a little. This is taken Columbia University, New York. Columbia was where they filmed Ghostbusters, but they also do research there, and this was in their real-time computing labs. We linked my nervous system live onto the internet and connected up to the robot hand, which was still in the United Kingdom. So this was across the Atlantic Ocean. When I moved my hand in New York, my neural signals moved the robot hand with interesting time delays, as we heard before, less than half a second time delay. The robot hand was in the United Kingdom, in England. So my hand moved in New York, my neural signals operated the robot hand in UK. When the robot hand gripped an object, signals were sent back from the fingertips across the internet to stimulate my nervous system. So essentially, as the hand gripped more and more, my brain was receiving this increased frequency, ding, 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 ding. And what I was trying to do was to open and close my hand to get the robot hand to just grip an object. And it worked very well, to get the pulses to almost die away to zero. So again, this is something that is useful for somebody that's had their hand amputated, but for all of us, you can extend your nervous system. You don't have to be a monkey. You can extend your nervous system as a human across the internet. The final experiment involved my wife again, and this is something you can all try later on tonight. What you have to do is to put very, very small electrodes into your nervous system, or find a friend to try it on, and you will find it is extremely painful. We had the doctor help us with this, and what we thought he was going to give my wife some anesthetic so it wasn't painful, but he said, no, I need to make sure that I've made a good contact. So with no anesthetic, he pushed the electrode into my wife's nervous system. She screamed, and he said quite calmly, I think we've made a good contact there. He pushed another electrode in the same way. She screamed again. We went back to the laboratory and electrically connected our nervous systems together. So when Irena moved her hand like that, my brain received a pulse. So when she went duk, 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 my brain received 3 electrical pulses. And back the other way, I moved my hand and it stimulated my wife's nervous system. So what we did was a very, very basic form of communication, telegraphy. If you think of Morse code, we were that, but in a very, very basic form. But we succeeded. Nervous system to nervous system, and if you count the nervous system as an electrical circuit, then it was brain to brain. But clearly, that's where we're headed here, not just nervous system to nervous system communication, but brain to brain communication. And that's where my research in this direction is going, is looking at bringing about brain to brain communication directly in parallel between humans. So I started off by using some words of Arnold Schwarzenegger from the Terminator, and I would like to conclude with some words from him, if that's okay. And that is that I have been a cyborg in the past, and as far as being a cyborg is concerned in the future, I'll be back. Thank you.